Hey, this is Mr. Mitchell with another video. Today we're going to talk about volts, amps, and something called ohms. Get to see what that is. So, when we're talking about electricity, it seems kind of magical. You flip on a switch, you push a button, and suddenly there's electricity. So, how do you get electricity when you turn a switch or push a button like on a flashlight? Well, it has to do with how ions flow. Now, you may remember that ions are these positively or negatively charged atoms. And the charges is what has to do with electricity. Like the different ends of a magnet, you may remember, like the different ends of a magnet, identical charges repel each other, like here. Positives repel, negatives repel, wherever that would be. I don't guess it's right here. But opposites attract. Positive, negatives attract, positive, positives repel. So you can make a charge move. Just like with a magnet, you can make something move. If something's magnetic and you hold a magnet over it, you're making it move. So it's kind of a similar process. You can get a negative charge to move away from another negative charge, or a positive charge to move away from another positive charge. And you can also get a negative charge to move closer to a positive charge. So, kind of in a nutshell version of how electricity moves is you can get lots of negatively charged ions to move if they have lots of positively charged ions that they're going to. So that's how you get electricity in a current. Now there's a lot more that we'll be talking about this, but that's what's happening here. You are controlling the current by the positive and the negative ions. You're kind of forcing them to go toward each other. Well, I don't know if you've probably don't have a full grasp of that yet, but here's a little bit about what we have here. You can measure the potential energy in something called volts. I don't think I have this anywhere else here, so I'll go ahead and type it in. You can measure the potential energy in something called volts. Now, by potential energy, if you have more negative charges, then you have more potential electricity. And potential energy per charge is something called volts. And I may have that here. Yes, volts measure potential energy per charge. And you can see that volts are going to be in joules over coulombs, and we'll get back to that in a little bit. But here you have, pardon me, a regular old battery. Well, AA's are very common. These small batteries are about 1.5 volts. About 1.5 volts, and it'd be a capital V. Now these large car batteries are usually about 12 volts. So these are measuring potential energy. The potential amount of electricity that can be gained through this at 1.5 volts is not the same potential electric energy that can be gained from this car battery at 12 volts. Now I'm sure you've seen signs that say like 1,000 volts or 5,000 volts that would be at like electrical power stations. So there's a lot of volts that could potentially cause electricity. And remember, it's potential energy. Batteries, what they're going to do is convert chemical energy into electrical energy. Now your book is going to say how there are electrolytes in these dry cell batteries on the left here, and the wet cell batteries on the right, where you actually have liquid electrolytes in here. But either way, the electrolytes are going to cause a chemical reaction And that chemical reaction is what's going to create the ions. You know, we talked about chemical reactions and how it can create ions. Here's roughly what is happening in a battery. Here at the top end you have all the positive ions that come from the electrolyte and the chemical reaction, and at the bottom you have all the negative ions. You may have noticed on a battery you can see positive. Oh, here's positive. This side's positive up here, and you can't see it, but this side's negative here. So what you want is all the negatives to flow toward the positive. You've got a barrier in here which won't allow it to do it. But whenever you flip the switch of, say, the flashlight here, what happens is it connects the circuit. And by connecting the circuit, all these negative ions will rush toward the positive ions. It creates a current of ions, and that is what shines here with the flashlight or with the light bulb. Kind of the same premise there. You're forcing the negative electrons, or you know what they will do. The negative electrons will go toward the positive electrons. Yeah, that's very, very smart right there. Very smart. The Edison, all those that came up with this idea. So let's go to this particular one, and I'll check my notes, see where we have. Okay, we have on this battery, one battery terminal is positive and one battery terminal is negative. Here's the positive. You can see it right here. So this is the positive terminal, and this is the negative terminal. And they have it to where on all batteries it's always the red that's positive and the black that's negative. So it's kind of universal that way. So whenever you have the connection here, when you connect something from one through, say, a car battery to another, then that gets the current flowing. Gets the current flowing from one to another. Gets the current flowing from one to another. Gets these negatives, in this case, going through whatever car battery or whatever it's going through, boat battery, to the positives, and that is creating the electrical current right there. Since the positive is attracted to the negative and the negative attracted to the positive, a current of charges flows from one terminal to the next through the bulb or through the engine or whatever you are sending electricity through. Now there's another term here. The rate at which these charges flow from one terminal to the next is called the current. Let me see if I happen to have it here. Yes, the rate at which it flows is going to call the current, and it is measured in something called amperes. That is not very bright right there. Let's see if I can get this on another page. And amperes are more widely known as amps. So what amps are, just to say it again, is how current is measured. The current from one terminal to the next is measured in amperes or amps. Now you'll notice this kind of an interesting analogy right here. We'll get to that in just a second. Current always flows in the same direction. It flows where the negatives are going to the positive. But conventional current, that's a term in your book, moves in the opposite direction. So the current is technically said to be going from positive to negative, even though you actually have negative ions flying through there. But anyway, most electrical appliances you plug in an outlet have the same voltage, which is 120 volts. I would type that in here, but it won't turn out to be anything, so I'll type it in here. 120 volts. Some things like light bulbs are meant to have different voltage. You ever notice that you can have a light bulb that is like 40 watts in a light bulb that's like 100 watts. The 40 watts won't shine as bright as the 100, but the electrical current is the same. The current that flows up through here is going to be that standard 120 every time. The current isn't what's changed. You have what's called resistance. In a light bulb, the filament is what makes the resistance. The resistance is used to change the amount of power. In a light bulb, this filament creates friction, and the friction doesn't allow as much of the current to flow through. So resistance is actually measured. It's actually measured, and we'll talk about these ohms in just a second. The current flow sometimes causes electrical devices to become hot, and I don't know why I'm saying that, but you actually have a measurement of resistance, and it's in ohms. So here you have this guy here that is resisting the flow of the current. Remember, the current is the amperes. The volts are the potential energy, how much electricity could go through. The amperes is what's the actual energy, more the kinetic energy, what is actually current that is going through, and you have the ohms or the resistance, which is trying to limit the amount of current that is going through. So that's kind of a good analogy right here. I like this little thing here. Now, you actually get a little bit of resistance when electrical devices become hot. In fact, this computer I'm at right now is a little bit warm. The moving electrons sometimes cause slight vibrations, and that slight vibrations cause heat, which is type of inadvertent resistance. Don't want to have that resistance, but it just is almost impossible to avoid. So we actually have a resistance formula. Now the resistance formula is going to be in something called ohms, and I think we mentioned that in the last slide. Resistance equals volts divided by amps. Now the amps is going to be the current, and it actually is I here. So the resistance is actually measured in ohms, and it's in some kind of Greek letter. I think this is omega is what I think this is, but you probably know more than I do about that. A resistor looks something like this, is a special type of conductor that's used to control the currents. It has resistance. They have a specific amount of resistance. For example, this one may be a 10 ohm resistor, and I don't think there's any way I can draw that omega sign very well here, but anyway, that's it. So if we were to calculate resistance here, we have a light bulb uses 15 volts of power and draws a current of 3 amps. So this should be pretty simple. We have 15 volts over 3 amps, which is actually going to be in I. So 15 over 3 is going to be the 5 ohms. And here's that crazy symbol there. So 5 ohms of resistance. Now in this case you are given ohms and you are given amps. So if you're given ohms and amps, what have you not got? You do not have volts. So in this case you'll have to solve for volts, and since we've done this many times, it will be easy to see that volts is going to be the resistance times the amps. And I'm really running short on time here, so I will not calculate this out, but resistance is going to be the measurement in ohms, so that would be 12, and the amps is going to be 0.5. Well, we can do this in our head. 0.5 times 12 is going to be 6. So that is going to be 6 volts is what that one will be. I hope you've learned a little bit about these volts, amps, and ohms. And hey, don't forget to read about this in your science book.